we discussed about the periodic signals and then how to deal with them using our Fourier series expansion. Okay. So, that means any signal which is periodic in time or in space also, in its argument, I should say that if any function is periodic in its argument, then it can be split into sines and cosines or shifted sines or cosines as a sum of many such functions. So, that is how we discussed it. And I mentioned in that segment that we will see two more ways of representation of the same thing, and in the literature you will find all these four kinds of representation, and you should never be confused about which one to be used where at, and then to convert one from the other. Okay. So, till now if to recollect, we have written something like this. Suppose we have a periodic signal xt. So, either you can write say as a summation of an cosine of n omega naught t minus phi n goes from 0 to infinity, or you can have an cosine of n omega naught t plus bn sine n omega naught t. Okay, so this is where we stopped with they are related. An squared is equal to an squared plus bn squared, and an cosine of phi n, did I write there? Okay, and bn is equal to an sine of phi n. Okay. So, this is what we had discussed, and then we said that we will see some more representation, two more to be specific, of the same thing. Okay. Okay. Now, to do that, what we will use is the Euler's formula relating complex numbers with sines and cosine, right. So, e to the power I theta is say cosine of theta plus I sine of theta. So, that is the Euler's formula, and that we can use to write these things in a slightly different form, and that is if I write say x of t is equal to real part of I will take summation of say Cn and e raised to say minus I n omega naught t. Okay. So, now if I do that, so what will be there? And just think about for a while, should this be a real number or a complex number? Think for a moment. I'll before, in fact, you should stop the video and think about this point. This is very important. Okay. And so I assume that you have stopped the video, thought about it, and now I am proceeding further. See, why do I say that it has to be a complex number? Let us see it. Suppose Cn I take as say an plus I times bn, and these ans and bn's are nothing but these things. Okay. And then I evaluate say Cn times e to the power minus I n omega naught t. So, how much will I get? So it comes to an plus I Bn times say cosine of n omega naught t minus I sine of n omega naught t, right. So, this is what you will get, but then if you expand it, you will get say a n cosine of n omega naught t. Then I will take the other terms, so that I will get I square minus, so plus here b n sine of n omega naught t. Okay. So, this is the real part which you will get, and for the complex thing I will get say plus I. So, this one will be b n cosine of n omega naught t minus a n sine of n omega naught t. Okay. Now, see this real part of this expression, is it not equal to this thing? Okay. So, that is what is the meaning of saying that Cn, the variable which is used there should be a complex number. It is very important to observe that. Okay. And so, that means now we have got another form of our representation, right. So, we had two and now we have got another one. So, all and then see that there is a point to be noted, that in every equation we have two unknowns per term, right. So, these are the two unknowns. These are the two unknowns in this equation, and here both the unknowns are sitting inside this. Okay. So, that is why you should always tell yourself that Cn has to be a complex number with those two real part and imaginary part being the unknowns. And you should also tell yourself that how with initial conditions these two are related, how that thing is related to the shifted version of cosine, and how that thing is in fact in a way manifested in the complex form. So, that is how whenever you see, always students have this query that why are we using complex number. So, the idea is the convenience, the mathematical convenience that the complex numbers offer, okay, in manipulation. So, that is why you are using complex number, just to have two unknown information in such a way that we can manipulate, and still we will retain this relative information between them, right. These are the phase and the amplitude. Here we will say how much of cosine and how much of sine, or you can say that how much of pull and how much of velocity. All such things, all the informations are clubbed together as this simple complex number coefficient here. So, that should be in fact, so this is giving you that cosine and sine thing is coming from here, and this gives you that an and bn terms. Okay. So, that means, so we have got another form, but then can we do even better, because that see that real part of a summation does not look very nice. So, another thing which we can do is we can write say that, sorry, I will use this, say xt, if we just do this trick, that to remove this real part business, we will take the complex conjugate and add them up. Okay. So, and divide by 2 by that way. Okay. So then we can get rid of the real business, isn't it, or doing the real part of a summation. So what we will do is, suppose now we will write say Cn. So what I'll do, this coefficient which I had written here, I'll write with a bar, because this form we will not be using much, so that this I'll replace with a bar, here also with a bar, so that here I can use just Cn, because this is the form most widely we will be using. Okay, in the literature also you will see this form a lot rather than the real part of a summation. So Cn times e raised to say minus I n omega naught t. Always keep in mind what omega naught is. This is related to the period of the actual function xt. So this is with a period of t, okay, and this t is related to somehow with this omega naught. Okay, now having written that, here what we will do is n is equal to from minus infinity to plus infinity. So once we do that, see, now we could just remove the requirement of taking real part of something. Okay, we just got rid of that. And then here what happens is your Cn will be half of an plus ibn, and when n goes to the minus side, C of minus n will become half of an minus ibn. That is the complex conjugate of this. Okay, and then so this Cn, if you define like that, and so these two terms will sum up and half will become 1. So you get exactly the same equation as before. Okay, and if we here, I should have even summarized that part. How? Okay, otherwise I'll do that here now. So now we have got all the forms, 4 forms of the Fourier series representation of any periodic function that we want to use. Okay, let me then summarize all the things what we have now. So I'll need some space, so I'll start from here. So if xt is a function with a period t, okay, so then you can write that as summation of an cosine of n omega naught t minus phi n, where omega nt is omega n is equal to 2 pi over t. Sorry, omega naught, right? So yeah, this is omega naught. So that's the thing, and then this runs from n equal to 0 to infinity. So this will be equal to an cosine of n omega naught t plus b n. So again summation n omega naught t, n ranging from 0 to infinity, n ranging from 0 to infinity. Is that fine? So that is equal to a real part of summation of Cn barred and e raised to minus I n omega naught t, n ranging from 0 to infinity, or you can say summation of Cn without a bar now, e raised to minus I n omega naught t, and now n goes from minus infinity to plus infinity. So these are the 4 forms which are very important, and then I'll also summarize here the other thing. So I'll just put a demarcation here. So this is one condition. Then the relationship are, so an is a n cosine of the phi n, b n is a n sine of phi n, then a n squared is equal to a n squared plus b n squared, that is obvious. Then what else? Okay, c n barred is equal to a n plus I b n, and c n is equal to half a n plus I b n with c minus n is equal to c n transposed, conjugate, okay, c n conjugate. And okay, so that is one. Then some more formula, I should write them. So here how you were calculating, C A naught was just the average of f t dt from 0 to t, and a n was nothing but 2 over t 0 to t f t cosine of n omega naught t dt, right? And bn was equal to 2 over t 0 to t ft. Why am I writing ft? I should be writing xt, isn't it? To be consistent, I'll change it to xt. Okay, here it's 0, this is xt, this is xt, here also, okay, so it's xt sine of n omega naught t dt. Something else should I write? Okay, this C n, I just want to write it in this only. Okay, so now C n will be nothing but 1 over t integral of x t e raised to I n omega naught t dt, right. So this will be xt cos n omega t plus I sin omega t. Yeah, so half has been cancelled here from 2, so that should be fine. So this is the whole thing which you should always keep in mind, and you should also be comfortable with all the conversions. You see, if any literature gives you any of the forms, and then you should be able to correlate what they actually mean, okay, and correlate also not only the algebraic forms but also with respect to what physically they mean when they represent like this with respect to our pull and velocity initial conditions. Okay, so that's which I wanted to discuss about the periodic input in a way, how to deal with them. Okay, so that means suppose you have a periodic function which is getting applied to the what do you call the system, then you can split that periodic thing into these harmonics, which are called harmonics or the sinusoids. So harmonic function, which is a simpler version. If you now remind yourself the complexity level, first was natural vibration, then came the harmonic. That means harmonic oscillation, if you apply harmonic output you will get, So, the idea is, even whenever you get a periodic input, you split that input into harmonics, and then you are having simpler problems where only harmonic excitation is applied, and then get the solutions, and then the solution should be summed up to get the full solution. So, that is how you should think of how to use the Fourier series in this context. And but then what about the next level of complexity when we add to this? If you remember, in the sequence, it was the case when f became aperiodic. Okay. Now, what happens when it becomes aperiodic? So, we will discuss that. So, the idea is the Fourier series will become Fourier transform, and we will see how to deal with them, and then how useful the Fourier transform becomes and when we try to use excitation which is not periodic. Okay. But before that, I think we should also spend a small segment on how to visualize these things to correlate the time and frequency in a way, what do I call, conversions. Okay. If you remember the first segment, when I introduced, I said that we should be able to think in terms of frequency and time. Now, we are in a situation where in fact we can discuss more clearly what exactly did we mean by when we said that frequency and time ways of thinking. Okay. So, that we will see in a segment, and then we will go to the Fourier transform segment. See you in the next segment.